Hello and welcome back to Calculus 3 section 17.4 on Green's theorem. This is a quality of life section because we don't really need this in life. We can compute the line integral and be done. However, these calculations, if the conditions are right, these calculations tend to be faster than the line integral. So if we'll see the whole pile of conditions are fulfilled, then you can use this calculation instead of the line integral calculation. Now, as this is not the honors section, we are not going to go through proofs, derivations, and stuff. We're going to go with the definition and the conditions and the formula, explain the formula, and then work some examples. So there are two flavors for the Green's theorem. There is the circulation form and the flux form. So we are going to learn those. So starting off with the definition for the circulation form. So definition, GT, Green's theorem, circulation form. And it has a whole bunch of prerequisites. So let C be a simple closed piecewise smooth curve. So be a simple closed piecewise smooth curve oriented counterclockwise that encloses a connected and simply connected region R in the plane. So let C be a simple closed piecewise smooth curve oriented counterclockwise that encloses a connected and simply connected region R in the plane. Assume the vector field F, which was our good Fg, where F and G have continuous first partial derivatives in R. Then, and finally, there is the formula. So the line integral over C with this little circle, I'll explain that, dot dr is the line integral the way we learned it earlier. And it can be calculated as the double integral over the region R as partial G partial X minus partial F partial Y dA. And before you freak out, how is it allowed for a single integral to be equal to a double integral? Please note that in the double integral region, you have the double integral over derivative, so one of the integrals cancels with that derivative. So you do have one integral and then one integral on the other side as well, right? If you are looking for the order of integration there. Not the order of integration, sorry, the amount of integrals. All right, so this part here in parentheses is called two-dimensional curl. That's and you will say that curl of f is equal to partial g partial x minus partial f partial y. That's a formula. So I'll box that. Two-dimensional curl. All right, so let's go to the shopping list of things we need in order for this to work, and then we'll deal with the rest. So you have a curve C. So when I drew a whole bunch of stuff yesterday, I said that if the region is in one piece, then that region is connected. And if it has no holes in that region, it's also simply connected. So connected and simply connected. Now, curve C is supposed to be counterclockwise oriented. Remember that curve C is always parametric equations, so it's going to go one way or the other. It has to be closed. It has to be piecewise smooth. Well, piecewise smooth means no sharp corners, but then the piecewise allows for some sharp corners, and we'll discuss that in a little bit more detail. And clockwise smooth, piecewise smooth, oriented, okay, connected, good. So all of these conditions, and that's your region R, that is enclosed with this closed curve C. Now, if you have a square or a rectangle or whatever, this is also okay as long as it's counterclockwise. For C, is it smooth? No, because of the corners. However, it is piecewise smooth because there are no corners and sharp edges on any of the four sides. Now remember what you are trying to do on the other side. You are trying to set up a double integral over the region, and you need the region to be something nice so that you can set up your integrals, right? So in a case of this, let's say a square ABCD, right, you would have your limits, right, if it's a square ABCD, and then, I don't know, dy, dx, or dx, dy, depending on what you guys get for. And this is, and the curl would go inside that integral. So once the problem is done, given to you, it is going to be some kind of a region. It could be a full circle, it could be half a circle, it could be, it's going to be something. Full circle, half circle, square, a triangle, so something that you guys can compute the area of in a double integral. And then all you need to do is to calculate the curl. Now if just one of all of the conditions that are there in this soup of conditions is violated, Green's theorem is off the table. You have to do line integral the way we did the line integral at the beginning of the chapter. So this is a quality of life formula which helps you compute things without going crazy with that long procedure. And finally, just this subtraction piece is called the curl, and it has its own formula. It calculates how much stuff spins. Curl, right? Curly hair, curl. So let's take a look at an example. Circulation of a rotational field. Are we going to have circulation rotational field? Well, of course, right? Circulation. So, rotational field F is given by negative yx on unit disk, which is unit circle. So parametrization for that puppy, well, x squared plus y squared equals to 1. That's the unit disk. And we are supposed to calculate the Green's theorem there. So what do we have? Well, first off, I have my parametric equations, which are cosine t, or cosine theta, sine t, which is a sine theta. Now, if you flip your notes back to 17.2, you will find me doing this problem long way through the line integral. Now, instead of doing the line integral, we are going to realize that we are on a disk, and we are going to compute the curl. So my domain here is a disk, and I'm going to compute the curl. So curl of F is equal to partial of G in respect to X is 1 minus partial of F in respect to Y is negative 1. So altogether is 2. So now I need the double integral of 2 dA set up from that disk. Well, hopefully we're going to use polar coordinates. Right? To set this up. So kick 2 outside, and we have the double integral of r dr d theta, and your circle up there is radius 0 to 1 and 0 to 2 pi, because we want the full circle. So when you integrate here, you have 2 integral 0 to 2 pi, and now r squared over 2 from 0 to 1 d theta. That's 2 times integral of 1/2 d theta from 0 to 2 pi. Well, a half will kill a 2, and when we integrate we get theta, plug in 2 pi, we get 2 pi, which is exactly what we got. Now, except now we used only 2 steps. Earlier we had a heftier calculation, right, to chase things around using line integral. So is the circle, no one ever said, they said just unit disk. They never said it's counterclockwise or anything. Well, this is where your knowledge of parametrization kicks in, guys. You know that by placing cosine first, you are obtaining counterclockwise spin. If you put sine first, you get a clockwise spin. So by coming up with the r to have a cosine first, right, you will ensure that you have a counterclockwise spin on this disk. And we're done. If you calculate curl for radial field, you will get 0. Now we did also get a 0 when we calculated line, oh no, we skipped it. No, we didn't do the integral, but so this is a rotational field. If you do the radial field, guys, radial field is like a sun, right? Sun that just shines the energy out from the center out in all directions. There is no spin there, right? The gamma radiation just goes whatever the center of the sun is to the surface of the sun, and then connect those 2 points and just let it go. So for radial field, if you want to do this, so radial field would just be xy. As soon as you calculate curl of the radial field, you will get a 0, because the partial g partial x is 0, minus partial f partial y is also 0, is a big fat 0. So when you do the double integral of 0, you will get 0. So radial field gives us 0 circulation. So we can say circulation of a radial field is 0. Circulation of a radial field is 0. So we will also say such a field is irrotational. That's what the name is. If curl is 0, field is irrotational. Such a field is irrotational. There is no spin. There is no spin. Curl is 0. So that's the first half of Green's theorem. What we are doing is we are making sure that the region we are enclosing is closed, simple, connected, simply connected, making sure that it's piecewise connected, piecewise smooth, and that actually gives us opportunity to set up the double integral. And we also need the first partial, continuous partial derivatives for f and g. Once we have all of that stuff there, we can replace the line integral with this. Now, for the first time, you see the integral sign with the circle in the middle. And that's just the notation that tells us that the curve C is closed. There is nothing else to it. It's not a special symbol. It's a not new type of integral. The little circle around the integral line just gives us, all this list above. This list, all of these conditions that are listed above are just encoded in that little circle that was placed over the integral. That's all it is. So it's just a new notation for the soup of terms. The second Green's theorem, which is the flux form, will have the same words as a condition, as just we are not going to have the curl, we're going to calculate the flux. We are calculating the divergence. This is a flux form, but we are calculating divergence and you'll see why divergence plays the role. So another definition, and this is Green's theorem, GT flux form. Now, anytime you hear the word flux, you are to think of infinitely many vectors poking out of the surface area perpendicular to it. The best way to picture this and experience it is think of the face of the fan, right? Fan is usually circular, right? Face of the fan, and all of the air is coming out of that fan perpendicular to the surface of where the blades are. So the blades spin, and we don't care about spinning, we care about the amount of air that it's coming out of this. So now you can talk about flux for all other things, as long as you have some kind of a field, magnetic, electric field, whatever kind of field you have, you can calculate the flux, because that's the it's one of the important things in science. It's actually one of the interviews that I was made aware of for a STEM position with a research company. They actually asked of prospective employees to calculate flux at the interview, because if you can't do that, obviously you can't work in that environment. So, these calculations are what's needed. So for the definition for the, theorem for the Green's theorem flux form, so we have same conditions. As before, then, and now we have the flux form, which is vector field dotted with the normal vector n. We can put a hat on it, ds, which is going to be the integral over the curve c f dy minus g dx, which in this case will be the double integral over region R, and our divergence df dx plus dg dy dA. So pretty much the same deal. As before. The piece in here is called two-dimensional divergence. And it's calculated as div of vector field f, which is just df dx plus dg dy. So that's a formula. Box it. There we go. Again, you have the integral with a circle. Circle is all that soup of conditions. The line curve C needs to be closed, needs to be smooth, piecewise smooth. Region it encloses has to be connected, simply connected. Has to be, curve C has to be counterclockwise oriented, and all that good stuff. So now, for this field, it should measure what? It should measure how much stuff you get to shine out of the system. What do I mean shine out? I don't care whether you talk about light or you talk about a fan. You have a surface of the fan that will emit the wind, right? All of those particles in front of the fan are getting pushed with a certain vector field forward because of the blades in the back that push the air forward. So we can calculate the amount of that stuff using the line integral over the vector field. So now over here we have again a way to compute the vector, the line integral, not through vector fields but through what we call divergence. So if we take a look at the radial field should yield values. Rotational field should not, right? So let's check. Radial field, if you memorize it by now, xy, and we'll do again on unit disk. So divergence of f is going to be 1 plus 1, which is 2. And we have exactly the same integral as before. So our double integral over the region R of 2 dA is going to be the double integral of, well, 2 kick 2 outside, R dr d theta because we are in a polar realm, 0 to 1 because it's a unit disk, and then 0 to 2 pi. And you have r squared over 2 again and all that stuff. So 2 integral 0 to 2 pi r squared over 2 computed from 0 to 1 d theta equals 2. You know, I'm just going to put 2 pi because we know what the answer is already. We calculated this long way earlier. So answer is 2 pi. More work goes here. Great. And if you try to do this on a rotational field, you will fail, because the rotational field is negative yx, and as soon as you calculate the divergence of rotational field, you will get 1 minus 1. These are not vectors, these, which is, right, because it was dg dx plus dy, so you get a 0. Sorry, I'll write it. Plus negative 1 is equal to 0. So the integral of 0 dA will give you 0 at the end, because the height is 0, so you integrate that. Now, rotational field gives us 0 on divergence, so we say that the field like this is source free. So flux is 0, which means, so if the flux is 0, right, so when two diverge, so when divergence of f is equal to 0, we say that the vector field is source free. And if you think about it, right, the divergence, well, you have already idea from Calc 2, you had the divergence there, but if I have a source, guys, think about the source of some kind, can be a sun, and then think about it emitting, and just like make a two-dimensional sun, and you just need to do 8 of these. There are infinitely many rays, but do we all see the divergence? Right, these two rays were this close, then they're further away, further apart, further apart. I don't care what kind of rays we're talking about, gamma rays, fine, right? There is the divergence there. This ray and this ray diverge from one another. So the divergence will calculate how much they diverge. So this is radial field. And clearly it has a source because you have divergence. right? Outside of the source, things diverge to cover everything around it. Now, when you have a rotational field and you have some kind of a disk there, then take a look at the vectors. They don't diverge like these guys. They're always at the same. They're the angles don't change. There's a spin for the rotational field. So the divergence is 0, and the divergence is, in this case, 2 pi for the radial field. So let's do another example. So let's say the line integral is given as 4x cubed plus sine y squared dy plus 4y cubed plus cosine x squared dx. So when you look at this, this is your f, this is your g, right? You had that in the formula right here. See, f and g. That's your f and g. Now note that there is a minus sign in here. Do we have a minus sign? No, we have a plus sign. So that means that each one of those will be picking up signs. So I'll say f is equal to 4x cubed plus sine y squared, and g is negative 4y cubed minus cosine x squared. And now we will calculate the... Oh, I copied the problem wrong. This is supposed to be a minus here, so these are still pluses. Sorry. We do have f minus g, f dx, f dy minus g dx. So we have our f and g. So we need to calculate the divergence. So to calculate divergence of f, remember that your f is f comma g, right? It's a vector field. So divergence of f, it's a partial of f in respect to x, well that's 12x, plus the partial of g in respect to y is 12y. So I have divergence. Now we are on the disk of radius 2. So on x squared plus y squared less equal than 4. That means we are on the disk. So now if I want to calculate the double integral, I will use the polar coordinates. The radius is 0 to 2. We want the full circle, so 0 to 2 pi. 12x plus 12y r dr d theta. Now you immediately see that you have x and y. That's not allowed. We know that x is equal to 2 from parametrization of the disk. Let me go up here, orange. So parametrization of the disk is telling me that x is equal to 2 cosine theta and y is equal to 2 sine theta. Cosine with x because we need counterclockwise. So now you will plug those for x and a y in here, and you will get the double integral 0, 0, 2 pi, and 2. And now you have 24 cosine theta plus 24 sine theta in parentheses r dr d theta. So you can kick 24 outside. You will be integrating r, so you are ignoring the cosine plus sine that stays as a coefficient. And you have your r squared over 2 calculated from 0 to 2. Still d theta. So this is equal to 24 integral 0 to 2 pi. And to compute this, it's 4 over 2 is 2. So we can actually, I'm just going to cross it out and say equals to 2, so that we can skip some steps. So now this 24 becomes 48. And all I need to integrate is cosine theta plus sine theta from 0 to 2 pi. And now, through the magic of me just looking at the answer without, computing this for 10 days. So in short, that 2 pi times 48 is 96 pi, and we're done. Now, do we have circulation for other shapes? Sure. If you take a look at your exam that you just got back, and you look at your problem 2 on the first page, your Green's theorem can be done on that shape. It's a piecewise, right? The Green's theorem can be done on the half annulus. The half annulus fits this because, yeah, I know it does have sharp corners, but it's piecewise smooth. So if you have it going counterclockwise, and then let's go 1 to 2 on the annulus, doesn't matter. I know your exam was up to 3, but who cares? If you take a look at this, then your double integral for, right, you will put your divergence of f inside, r dr d theta, and your radius is going to go from 1 to 2 because you only have this portion to worry about. Now your theta is going to go 0 to pi only because you only want a half of this. Your exam question, I think everyone got it. I think it was 20 pi or something like that. 20 pi? Maybe 1 or 2 people messed it up. But it was 20 pi for the second problem. Now, for the problem in over there, you will have a different thing in here, and this is a 3, and this is 2. No, this is still pi, because still half. So 0 to pi, 1 to 3, and then whatever blurb goes in the middle over there, r dr d theta. And you should come up with 20 pi as the answer. That's an amazing final exam question, because it deals with a lot of stuff. Especially if it's a Green's theorem, you get to repeat the exam question, right? And then instead of having whatever guts over there, you're calculating divergence. So it's cool. So again, it's a quality of life section where instead of calculating line integral with all of those substitutions and headaches and parametrization you guys have to do, you actually look at the region, which could be a square, a rectangle, a circle, a half a donut and donut, or something like that. Oh, annulus. Could be triangle, could be trapezoid. And then you can set up your double integral and compute the divergence in the double integral, or for the circulation form, you calculate, right, the curl, and that's it. There are a few of these exercises you guys can try at home. It's homework. And then that's it. I hope you're not disappointed. Bye.